To record. There we go. Perfect.
I didn't do anything.
Oh, okay. Don't worry about it then.
Okay. How's everybody doing? I'm gonna get some water. I'll be back before 11:05. I think one of the things that we should talk about is like how to do the questions, right? Questions and answer.
So generally what we've been doing is having people put questions in the chat and then going through the questions at the end of the presentation. And that
Uh,
seems to be working well.
yeah, I can also, I don't know if when people raise their hand, they go to the top of the thing, right? Like they appear to me. I can see them on the participants thing.
If you want to try that, then go for it.
Okay. Yeah, I guess maybe I can make like say something at the beginning saying, if you have quite something that you want to ask immediately, just go ahead and ask it. It's very informal. Like it's not a super, you know, structured thing. It's just like a story that people can interrupt at any time. So yeah. Okay. I see that there is a message from one of the participants saying that the audio is breaking up. Can everybody hear me well, like as I talk right now? Because okay. Perfect. Yeah, I think I actually was muting myself a bit earlier, so it might have been that. Hmm. Okay, almost time. All right, my clock says 11:05 right now. So I'm gonna begin today's presentation. And this is the second lecture in the week about pulse processing and data analysis. And we're gonna talk about correlation analysis. So a bit about myself. My name is Stefano, and I am a third-year PhD student at the University of Michigan. And today's talk, I wanted to show kind of like what it is, giving you some context, is about interpreting plots that show some kind of a X versus Y result. So this is going to be an extremely general talk that is not going to talk about anything specific, but rather about how to analyze correlations across the board. So whenever, there are many types of plots that you see in many different settings. So this is not really regarding any type of figure, but it's really when you have two variables, which you regard one as the independent variable and one as the dependent variable. Usually we take the X to be the independent, so the one that we have control over, and the Y as being the dependent variable. I'll show you how to create this plot, how to interpret these plots if you find them in the literature, and what do we mean by correlations between variables. I know some of this material might be, you might have covered already in some probability and statistics courses. Some of it might be new. And just as a bonus for the people who have already covered most of the stuff in their courses, I have included in the last slide something a bit more advanced in correlation analysis. So these are partial derivatives in correlation analysis. And this could be interesting, so stick around even if you have seen most of the material at the beginning. So as I said, the main motivation for this work is that correlations are really some of the most important things that we do in experimental study, in scientific studies. It's not the only thing we do. I wanted to make a general statement at the beginning saying that everything in science is about correlations, but that's not true. There are other parts, for example, finding the structure of things or the reason for things happening. But of course, in the most technologically interesting part of science is discovering correlations between things. For example, some examples that I show here are how much does the resistivity of a material change with temperature? Then of course you can develop some kind of technology or some kind of feedback loop that allows you to find how a material will behave under different temperatures. In this case, the temperature would be the independent variable and the resistivity, the dependent variable. In this case, the correlations are quite linear, quite simple, but they don't have to be. Another type of correlations, a bit more complicated, is the lower left plot, where we see, for example, this is a very important one in nuclear engineering, the correlations between the cross sections for fission of uranium-235 as a function of energy. In this case, you can see that there is not a simple linear correlations, but we do recognize some structure in it. Something much more complicated that cannot be described in simple terms as a line or a sample function is, for example, the magnetization of a sample as you change the magnetic field. All of these are what we call correlation plots, which show as we change one variable, how does the other variable changes. And one of the best ways to describe this plot is by looking at the derivative. Now, the derivative is something that everybody has encountered in the first calculus courses as the slope of a curve, but it has a much deeper meaning, which shows how much does one variable change as I change the other variable. So, as I said, as I also say in the last paragraph there, the relationship that we can analyze through these correlation plots does not have to be a simple function, and does not even have to be a function defined like in your elementary courses in calculus at all. It can be something that doesn't pass the vertical test. For example, these loops that you see here for the magnetization. Now, the applications for this work are going to be very broad. You're going to be able to apply this to pretty much any field that you want to study. One thing that I show here is, for example, something that I have done in the past. Actually, let me. So one of the things that I wanted to show you is something that I've done here in the past, which is looking at the correlations between gamma rays and neutrons emitted following fission. Here, you can see that there isn't nothing special about the independent or the dependent variable, because in this case, what I do is I switch the role of the two to find what the correlations are in a very broad sense. The applications of correlation analysis are, of course, also important to compare different experiments where, for example, the axis might change, or some biases or errors might be introduced, as well as, of course, into performing error analysis by knowing how the errors affect the correlations that we observe in the experiment. And lastly, by having a good grasp of the correlations between variables, we can create hypotheses that can tell us why these variables are correlated to each other and what are the laws that determine this. Just a quick overview of the next few, or well, of the whole slide set. I'm going to be beginning talking about random variables and uncertainties in variables. Then we're going to talk about one-dimensional and two-dimensional histograms. We're going to move on to regression analysis, and lastly, causal correlations. So let's talk about statistics and probability in general. So a probability distribution just describes the probability that something will happen. I know this is kind of a tautology, it's not really applicable in real life, but there are actually two different interpretations of what probability means. In one case, we're talking about the frequency distribution of something that can be repeated many, many times. So for example, what is the probability of throwing a 1 when you throw a dice? You simply take the dice and throw it thousands of times, and you count the number of times that you have observed a specific outcome. And in another case, we're talking about the likelihood that something will happen. So for example, what is the likelihood that the Kansas City Chiefs will win the Super Bowl this year? Well, before the Super Bowl, there was some probability they would win. And after the Super Bowl, the probability just collapsed to a certain value. Now, these are two very different interpretations of probability. And what we're mostly going to be concerned here are the first kind, the things that can be repeated many times and can be analyzed. So not so much an assignment of a probability based on our knowledge and our confidence that something will happen, but mostly with probabilities that derive from a repeated experiment. So probability distributions, I'm sure that some of you have seen many of these before, can have many shapes and forms, and they're only constrained by two things. They always have to be positive, and they have to be normalized to 1. So for example, a probability distribution can look very simple, something like that, or they can look something like this, as long as the area below these two curves is 1 and the same for both of them. Now, a special example of a very important probability distribution is the normal probability distribution, or the Gaussian distribution, which arises in all fields of math and science and all the important fields of technology. And this distribution here is probably one of the simplest distributions you can find, and is also called the bell-shaped distribution. So this distribution, as we said, must be always positive, and the area under this curve is equal to 1. We describe it giving the center of this distribution, called the mean, as well as the width, or the standard deviation. And this is actually something that we're going to explore in more depth in the next slide. Well, so now that we have a bit more in-depth understanding of probability distribution, although that was just a refresher, we can talk about random variables. So a random variables is something that defines a probability distribution. It's something that that when sampled many, many times would define a frequency distribution. So a random variable is, for example, the outcome of a dice throw, or it can be anything that does not have a precise value, but it can rather have many different values, where, depending on how many times it's being sampled. In the plot here, I show a rather complicated random distribution. In this case, I show the cross-section of gamma and neutron emission from uranium. In this case, or for gold. In this case, what the probability, the random variable in this case is not the curve itself, but it's each sample point indicated here by this circle. So each data point in this case is itself a random variable. And why do we say that? Because as you might have seen in your introductory courses, in physics introductory courses, whenever you make a measurement, you never can tell with infinite accuracy what the measurement yielded, but you always have to give some kind of uncertainty or some kind of width to that data point. So whenever you see a data point with uncertainty, what you should think about is that sample there is actually sampled from a normal distribution that we covered in the last slide, centered at where the dot is placed and with a width given by the error bar. As you can see, then random variables appear in all fields of all investigations of both experimentally and theoretically, just because they represent the uncertainty on all the numbers that we find in the real world. So if we wanted to find the probability distribution for a certain random variable that we're trying to investigate, the way we would do it, assuming that this is that we can repeat the experiment many times, is the one-dimensional histogram. So the one-dimensional histogram simply says that we want to take an experiment and repeat the same setup many times and bin the outcome according to some binning. So for example, if the outcome is discrete, the binning is quite obvious. You just simply bin the number of outcomes, but the outcome can also be continuous. In this case, we would have to put bins that encompass some density of outcomes, so some area of outcomes. The two examples that I show here are the probability of throwing a certain outcome with a die, for example, shown that, as you can see, of course, for a normal unbiased die, should give a uniform distribution. And the way we interpret this histogram is simply by saying that after repeating this experiment 10,000 times, the probability or the frequency of any given outcome is uniform. It's the same for all of them. Something more complicated and something that's more interesting physically is, for example, a histogram that can be formed by looking at the energy deposited by a gamma ray in a material. So as you can see, by shooting thousands of gamma rays on a material and recording the energy deposited, we find a histogram that looks something like as shown here. And this histogram here gives us a lot of information about the interaction that's taking place inside the material and can be used, for example, to infer what type of interactions, what are the laws that determine the interaction between gamma rays and the material, in this case, electrons. Now, when we look at a 1D histogram that I've shown here, we have shapes, we have curves, we have points, but we don't have really data. We don't have something that we can easily communicate to other people. So how do we interpret, how do we analyze one-dimensional histograms? Well, in this case, we introduce, rather than the concept of probability, the concept of statistics. So statistics is the field of analysis of histograms. I don't know if this is the actual formal definition that you'll find in the dictionary, but this is how I like to interpret it. One way to think about this is also, imagine if you were calling a friend and you were trying to describe the histograms that we saw in the previous page to them over the phone. And let's also assume that, for example, this is an international call and you want to spend as little time as possible on the phone. So you want to give, in the shortest time possible with the least amount of information, you want to give as much as you can about this distribution, about this histogram as you can. The parameters that you would tell over the phone, so these parameters that fully describe or approximately describe the histograms, are called the statistics or the statistical parameters that describe this probability distribution. So there are some pretty usual parameters that we usually use in any kind of description for probability distribution, and they are usually called the moments of a distribution. There are many moments defined. There is always a word before the moment. Some people use the central moment, the standard moments, the factorial moments, the cumulative moments. Like, there are many different types of moments. In this case, I'm going to talk about the central moments, which I'm sure are also the ones that most of you are familiar with, because not only they are the ones that are most present in this area of research, but they're also the ones that you would hear about in the news or in books when people discuss and argue over distributions and any kind of data. So, if I wanted to describe a distribution to somebody using statistical parameters, these are the parameters that I would tell them. I would let them know what the mean of the distribution is. This would represent something like what happens if I average over many different samples from the same distribution. A different parameter that I can use is, or second parameter that I can use after giving them the mean, is how wide this distribution are. And this is either in terms of the variance or in terms of the square root of the variance, which is the standard deviation. So if I give somebody over the phone simply the mean and the standard deviation of a distribution, they would be able to tell, to have in their head an image of a distribution that is centered somewhere and that has a certain width to it. If I want to give them even more information using statistical parameter, a third thing I can give is the skewness. The skewness describes how asymmetric this probability distribution is. So for example, in this example that I've been working with here, this probability distribution, if I only knew the mean and the standard deviation, I would think maybe that it looks something like this. But if I wanted to relate also that it's very asymmetric, I would also give this skewness parameter, telling the other person that the distribution is rather skewed to the right. Last parameter that has a name, of course you can extend these central moments up to any order you want, but the last one that's being named is the kurtosis. In this case, this is the parameter that describes how spiked this distribution is. And it's kind of related, of course, to the standard deviation of the distribution. The smaller the standard deviation, the more spiked the distribution is. But this is also about how the tail behave with going away from the mean. So these are the one that I showed in the last slide, were the general or the standard moments of a distribution, the standard descriptors that you would use whenever nothing else comes up better than that. But of course, if I had a general distribution, if I had any distribution, sometimes these usual moments are not the best way to describe it. And it is up to you, to whoever collected data, or whoever is analyzing the data, to come up with better statistical parameters to describe this distribution. So for example, if I wanted to give a distribution of this curve to somebody in terms of statistical parameters, it wouldn't make a lot of sense to use the mean, which would probably fall somewhere here, or the standard deviation, which would fall somewhere here, simply because it would not describe very well this distribution, which after only two parameters would look something like that and would resemble nothing of what I'm trying to describe. Better parameter would indeed be, for example, the ratio between the height of the Compton distribution at the center versus the Compton distribution at the top. Or, for example, the width of the Compton edge, or the location of the Compton edge. So a few parameters, when chosen appropriately, can fully describe a distribution much better than the standard parameters that you would find in statistical books. Regardless of how you call them, regardless of what you use, the central moments or other types of moments, or these application-specific statistical parameters, all these are simply ways of compressing information and giving the most useful information rather than giving the entire curve to the other person. Okay. So now that we have talked about the 1D histogram and the properties of one-dimensional histograms, we now want to talk about two-dimensional histograms, because remember, what we're interested in the end is to finding correlation between two variables. So how do we form a two-dimensional histogram? The process is extremely similar. In this case, instead of recording a single outcome for a repeated experiment, as we did for the 1D histogram, we do an experiment which has at least two outcomes, and we record those two outcomes at the same time. Basic examples, again, could be, for example, the dice roll, in this case using two dice, and every time the two dice are rolled, we record the outcomes of each die separately. In this case, I show here the probability, this histogram as a two-dimensional histogram, where the two axes at the bottom represent the two dice, and the axes coming out of the page represent the counts. As you can see, of course, the two dice are uncorrelated to each other. The first die doesn't know what happened to the second die and vice versa. So the probability distribution is again what we call a two-dimensional uniform distribution over this area. Of course, the fluctuations that we observe here and in the previous plot are simply because these frequency distribution, these histograms, will converge to the probability distributions for an infinite amount of repetitions. In this case, this was 10,000 dice rolls. So we've only gone some ways into approaching this asymptotic behavior of uniform distribution. In this case, looking at this 2D histogram here, we see that it's a surface, it's rather uniform. So it's interesting to look at, to see that when something looks rather flat, the two things are uncorrelated. Let's look at something instead that is very highly correlated. And by the way, of course, I haven't told you yet what we mean by correlations, but of course, we should think about whether the two outcomes know of each other and can influence each other in any way. In this case, I show you what happens if I have a gamma ray beam that impinges on a material, and we then record not only the energy deposited in the material, so the recoil energy of the electron, but we also record the photon energy outgoing from the material itself. And when we two-dimensionally histogram that, we see that this distribution does not look uniform at all, but rather has very pronounced structure in it. Again, we cannot look at this distribution and infer quantitatively what are the correlations between these variables. And this is where, again, we have the use of statistical analysis and statistical parameters to describe these distributions. Well, 2D histograms are actually what we call, are composed of three parts. There are the two parts that they inherit from the one-dimensional histograms, plus a correlated part that describes the things that happen between the two distributions. So if you wanted to visualize a 2D histogram, shown here in the figure, as a density of plots, as a density plot, you see that we can form two one-dimensional histograms from a two-dimensional distribution, which we call the marginal distributions. So if we look, for example, at a projection of this distribution on either of the axes, representing one of the two variables that we're trying to correlate, we see that we can form two one-dimensional histograms that we can describe in the same way that we would have if we just had that information. However, there is extra information that is not captured by the two marginal distributions. And this is actually what we call correlations. So whenever we think about describing correlation between variables, we are interested in finding these extra properties of the two-dimensional histograms that cannot be captured by describing the one-dimensional histograms independently of one another. So let's start with a simple example. A simple example here is what we call a multivariate normal distribution. And this is probably the simplest case of a normal distribution of a correlated two-dimensional distribution. This distribution has the property that as one variable changes, the mean of the other variable changes as well. As you can see, one way to describe this plot, for example, I could create the two marginal distribution and describe fully them using the central moments, and then perhaps give some kind of parameter describing the angle of this ellipse. So even looking at this, by the way, the same figure plotted in two different ways, both in a three-dimensional and as a density plot. As you can see, what is different about the two, normal two-dimensional histogram where the two variables are uncorrelated from each other, and what we have here is that this probability density has a tilt to it, showing that the probability distribution of one variable actually does depend on the value of the other variable, and they are somehow correlated. So giving the angle of this ellipse with respect to some fixed coordinate axis is an interesting way to look at it. It's definitely an interesting way to visualize the result, but it's not probably the best quantitative way to do so. A much better way to do it, and a much more general way to do the correlation analysis, to find the correlation between variables, is to instead look at the regression. So to look at different projections of this probability distribution, of this two-dimensional histogram. Going back again at the simple and the same example that we saw earlier, We can find the correlations by cycling through, so going through each of these vertical slices of one variable. So these are slices that have the same value of x and all the values of y. So fixing the value of x and looking at all the values of y and looking how the distribution changes with x. So for example, looking at a slice of the distribution, where of course these variables have no meaning, they're simply mathematical constructs, you can see that we obtain a distribution that can again be described using some kind of statistical parameters. You know, as we talked about earlier, we can talk about the skewness, and talk about the standard deviation, the mean. And for each of these slices, we can assign the statistical parameters. So for each slice, we would have something like the mu, sigma, so the mean, the standard deviation, the skewness, or we can also have other parameters that we have made up. I don't know, this could be the area after a certain amount, like after certain points to the right of the sample, or really anything arbitrary that you can come up with that you think describes this distribution better than the central moments. Then we repeat this procedure for each and every slice of the probability distribution here. Let me use the same color so that it is clear. After cycling through each of these slices and finding the statistical parameters of interest, we obtain a plot that's shown here, where one of the axes is where the independent variable axis, the x, is kept fixed, and the dependent axis shows a statistical parameter of the distribution of y. So for example, in this case, I show two statistical parameters that we've selected from that distribution, one of them being the mean of y for selected slices in the x direction. As you can see, this statistical parameter has a rather pronounced correlation with x. And this is exactly what we talked about at the beginning, how to form these correlations, how to investigate correlations between two variables. So as you can see here, we're investigating how the mean of a distribution changes with the value of the other distribution. Another possible correlations that can be formed is by looking at, for example, another statistical parameter, in this case being the standard deviation, so the width of the distribution for a function of x. And just by the choice of the distribution that we have selected, we see that in this case, the y distribution and the x distribution are uncorrelated in terms of width. So just to give a summary so far, there is a few slides after this. In order to find the correlation between variables, we have to collect data from some experiment where we have more than one outcome, and collect the data for both variables at the same time. So we need to collect the variables on the x parameter, on the y parameter, as well as both outcomes at the same time. This is done so that we can find both the one-dimensional histograms and the two-dimensional histograms for the distributions. We then want to describe each of those one-dimensional histograms in terms of statistical parameters that we think, knowing the data, knowing the distributions very well, best describe the data. So usually what I think about is the least amount of statistical parameters is best. And once we have this set of statistical parameters, we can form correlations by showing the correlations between each of those statistical parameters as a function of the other variable. Of course, we can then repeat the procedure where we switch the values of x and y, so that we can find how the two variables do not only affect certain parameters, but really all the parameters that describe the curve for each slice. Okay, now going a bit more in depth into the correlations, we see that the result of these correlations can take many different shapes and forms. So for example, in the simplest one being the linear correlations between the two, as we saw, for example, in the mean of the distribution. So if the statistical parameter shown here were the mean, it would be the same as we saw earlier. Now, looking at a different combination of the statistical parameters, or looking at a specific statistical parameter, one can find linear correlation between the two variables. Sometimes this correlation are not going to look exactly linear, but they might have some kind of polynomial result to them, or they can have a complicated structure. So in this case, this plot was actually done using the difference between two to exponential. So it's a much more complicated functional space. However, we are going to focus for the rest of the presentation on linear correlations. Linear correlations are by far the simplest one to describe, and they are also the simplest one to understand. Now, when I say that we should focus on linear correlations, I don't mean that if something is non-linear, we should just give up. There are many ways to take non-linear correlations and make them linear. One way to do it is, for example, to express the correlation, the statistical parameter that we're trying to describe in terms of a combination of statistical parameters. So instead of looking only at standard deviation, perhaps looking at standard deviation divided by the mean to some power. And if we are smart in the choice of what we put on the y-axis, we can often find a linear correlation between things. Another way to do it is by correctly choosing the axis of our plots. So this is something that I'm sure all of you have seen before, but of course there are different combinations of using linear and log scales per plot in order to make some functions appear linear in the axis. So for example, using a linear scale would make all linear plots appear linear, whereas using a log scale would make every power law distribution look linear in this. So whenever you have a non-linear distribution, whenever a statistical parameter of one distribution there is non-linearly with the other, you can try to change the axis until you find something that looks linear. Now, this doesn't have to apply throughout the whole range. You can, of course, describe the correlations in different ranges using different axes and simply give the slope in different regions. Why do we want to use linear correlations? Well, linear correlations are extremely simple and powerful. And the reason for that is because they can be described with probably one of the nicest functions out there, which is the covariance between two variables. Imagine the covariance, as I said earlier, there are central moments, the mean, the standard deviation. You can imagine the covariance as being a half step between a mean and a standard deviation defined for a two-dimensional distribution. So it has all the nice properties that these moments have. And it's also one of those operators that have been studied for centuries. So we know a lot about it, we know how it behaves, and we can correct for any experimental biases or uncertainties that might arise in an experiment. What happens, one way to form the covariance between two variables very easily is by using the mean of a distribution as the statistical parameter that we're trying to analyze. In this case, you can see that the covariance between two variables is simply given as the slope of the mean of one of the distributions as a function of the slice number or the value of the other one, multiplied times the variance or the standard deviation squared of the other distribution. So it has a very nice also mathematical expression to it. Okay, moving away from linear correlation, let's talk about something that people usually talk about, with the difference between causation and correlations. So we're not always interested in causation, but this is actually something that might be interesting if we're trying to discover new things. So let's say we're trying to discover how one variable affects another. We're not really interested in how two things correlate to each other, but rather how they cause each other. And the best way to do this is by looking at correlations and trying to understand whether these correlations are of causal nature or are simply caused by a common dependence on a third variable. So, for example, an example that I show here is that I don't know if this is true. I found it online in a website talking about this misconception in causation and correlation, is that the number of shark attacks and the number of total sale ice cream are strongly correlated to each other. Now, this doesn't mean that if we suddenly decided to start selling ice cream at any point during the day, there's going to be more shark attacks, but rather that both of these variables are dependent on a third variable, in this case, the temperature outside. So the number of shark attacks, of course, is going to be dependent on how many people go to the beach and how many people go swimming, which is strongly correlated to the temperature. So in the summertime, it's going to be increasing. And ice cream sales, same thing. So it's going to follow the same thing. So even though the number of shark attacks and the number of ice cream sales are not causing each other's behavior, they are independent of each other. they would appear to be correlated to each other because they share a common causal factor. As I mentioned at the beginning of the presentation, I wanted to show here, how do we handle this? If we knew the dependence of each of those variables with a third variable that we think is causing the behavior of those two, we can use something that is done pretty regularly in normal calculus, which is to transform the total derivative in terms of partial derivatives. So of course, if we know that the two variables depend on a third variable a, we can express this as the partial derivatives of the functions. If we wanted to do the same thing using the covariance, again, covariance is a great parameter that you should always strive to have in your analysis. We see that the covariance between two variables, each depending x and y, each depending on a third variable a, can be expressed as the covariances between x and y for a fixed a. So this would be the actual correlation or causations between x and y, which vanish if the two are uncorrelated, plus correlations between the two variables with the third parameter a. And with that, this is actually the end of the presentation, and I hope this introduction to correlation analysis will be helpful to you in the future, and especially this use of the covariance as a statistical parameter, and its use is also in finding third variables that might be causing these correlations in your data. With that, I think I'm going to open up to questions, and if anybody has any question, please post them in the chat. And this can also be like any kind of questions you have. If you want to discuss some variables that you want to correlate, or or any clarifications, of course, you can post them there. Otherwise, this is the end of my talk. Is there a quantitative way to describe? Oh, sorry, wrong screen. Slide 21. Is there a quantitative way to describe the covariance? Yes. The covariance is described both in this way here. So if I had two variables that I'm trying to describe, and I would have the slope here, with mean of x versus y, I can describe that with a slope, and then multiply that by the variance of this distribution. So we can imagine that this y actually follows some distribution, and we can multiply by that to find the covariance. Another important definition of covariance that you might find, and this actually shows some of the most important properties of the covariance, is that the covariance between x and y is given as the product moment, or the product mean of the two variables minus the product of the mean. So this is sometimes like a good mnemonic to remember. This is that the covariance is equal to the mean of the product minus the product of the means. Because it has this shape, this mathematical form here, actually the covariance has a very interesting property of being bilinear. And same as like linear functions that are extremely nice to work with, bilinear functions are also very nice to work with. So that's another reason why we always try to look at the covariance between things. Any other questions? Let's give it maybe like a minute or so, and then Will, what do you think? All right. It looks like then this was the only question. It was great to give the talk. I hope you have learned something, or I hope you have refreshed maybe the things that you already knew. These presentations, I think they're going to be posted on the Google Drive, and okay, actually there is a new question from Eli. Okay, so the question is why the mean is our statistical parameter and not something else? That's a good question. Why are we looking at the mean in this case? Well, because if we want to use the covariance, we have to use the mean. Of course, we don't have to use the covariance. We can look, for example, if we wanted to correlating the skewness of the distribution of y in terms of x, if this is something that we're more interested in, like how the distributions become more asymmetric as a function of the other parameter. But in this case, we would not have access then to this nice function, the covariance. But of course, you can always just express, in this case, what you would do is simply go and express your final answer as this slope here. So as your correlation between these parameter that you've chosen and the x. But that's where you wouldn't stop. You wouldn't go on to talk about the covariance after that. Does that answer your question, Eli? Yeah. So an example not using the mean. Let me find some white space here to talk about that. So for example, let's say like a real life example. Yeah. So let me answer the question from Ila first, and then I'll get to the question from Gia. So a real example could be, for example, a distribution that when plotted as a two-dimensional histograms looks something, for example, like that. I don't know if you have seen already the talk on PSD. I think there have been some talks about PSD. But for example, if we plot the PSD parameter, which is just defined as the tail over the total of a pulse, we can distinguish between neutrons and gamma rays based on this parameter. We can plot that as a function of the energy deposited. And what we would see is a plot that looks approximately like this, maybe like one here and one here, with this being gammas and this being neutrons. Well, one thing that we see is that if we go through each of these slices, let me change color to be clear, each of these slices, how does this distribution, the mean of this distribution change? Well, really not that much. So you can say that the mean of this distribution remains quite the same if you look at the mu of the PSD. So it's an interesting parameter to look at. You can say something about that. But also important is to look at how narrow it becomes as a function of the deposited energy. So if you look at how good the PSD becomes as a function of energy, you would see that it looks something that becomes smaller and smaller. So in this case, you would have a real life example where we would plot not the mu, which is interesting, but doesn't change as much, but rather the sigma. So rather the standard deviation or the width of this distribution as we go on and on. And this is of course the reason why our PSD discrimination becomes better and better as a function of energy. We can, of course, I just chose this example. There are many more that you can do. As I said before, if you want more interested in the asymmetry properties of things, you would use the skewness or some kind of made up parameters that you've made up, that you created. Question, maybe I missed it, but how the covariance is different from correlation? Can we say the covariance is the measure of correlation? Absolutely, yes. The covariance is a measure of correlation. It's actually, you'll find in some, if you go also just on Wikipedia and look up what is the difference between covariance and correlation, is that two things can be correlated with each other, but have a covariance of 0. So the most important thing is that the covariance describes the correlation between the means of things. So between the mean average values of the two distributions. So if the correlations are between the other statistical parameters, then the covariance will not be the appropriate statistical parameter of that. So it's a measure of the correlations in the means. It's not only a measure of the correlation of the means, it's a measure of the linear correlation in the means. So if the correlations look like that, we decide that we want to use the means because we want to use correlations, we want to use the covariance to describe them, mu of x as a function of y, but this plot looks like that. Well, it turns out that the covariance of this would be approximately 0. So in this case, it would not be, you would not use the covariance. It would not be the best thing. Or rather, you would use maybe something else. You would use some other parameter here to describe that. For example, you could fit each of these slices using a quadratic and then plot the coefficients of plot the coefficients independently on this plot to show the correlation. So maybe one would look like that, one would look like that, one would look like that. So that's the difference between covariance and correlation. Correlation is kind of general term. How does one statistical parameter changes as the other variable changes? And covariance is how does the mean of one parameter changes linearly as the other parameter changes. So much more precise, but it turns out to be very applicable in many different cases. Okay. So if there are no more questions, it's 11:51. We do have like another 10 minutes, but otherwise we can, I see that a lot of people are leaving. Yes, question from Jake. You are asking, how come two variables that are non-linearly correlated to each other give a covariance of 0? So what you do in the covariance is you're looking at the mu of one distribution as a function of the other one. And let's say that this mu, each of the data points that we would put on this slide here, on this plot here, is of course a slice of the two-dimensional histograms as a function of x. And let's say the distribution looks like this. So then you go to your code of, your preferred code for fitting functions, and you ask, you ask it to fit a linear function. So you can use Mathematica, you can use MATLAB, Python, whatever. And what that is going to do is going to try to do a least square fit to these points. So it's going to try to fit a function, maybe this function or that function that minimizes the distance of the function to each of the points. Or rather, it's going to try to minimize the square of this distance. This is called the least square residual fit. And it turns out that for something purely quadratic, or for something, there are special cases in which you can have a very noticeable correlation, but it just so happens that the line that minimizes this least square fit is the line that goes right through flat to these points. So it may be, for this example here, any other slope, or more pronounced slopes, would have too much of a difference with these endpoints here and these points over here, and it would not be the best fit. So it just, from the fact that it's defined as the least square fit of the linear least square fit of the mu of one distribution as a function of the other. Yeah, so it's a deficiency of the covariance in only being able to describe things with only one parameter. It's great because it does that. It's great because being able to describe things with one parameter is excellent, but sometimes you can be tricked. Mm-hmm. Okay, 5 more minutes for questions. If anybody has any, doesn't matter. Like any kind of question, it can be on anything that I presented on. It can be something. I don't know if you have a project that you are working on right now, and you're like, I don't know which parameter to choose. I don't know how to describe this correlation. We can talk about that for a few minutes if you'd like. I'm sure that everybody would benefit from an example as well, another example. Otherwise, you can just